know some of the logic behind the analysis of the variance in ANOVA, let's actually look at some examples, look at some output, and practice our interpretation. So without further ado, let's get into it. We are going to go from T to F and look at the F distribution. Yay! We'll have a sum of squares refresher, look at an ANOVA table output, hypothesis testing for ANOVA, pairwise comparisons, and ANOVA and R with some real data. T-tests have T-statistics, ANOVA has F-statistics and an F distribution. And no, I'm sorry. The idea behind the hypothesis test is still the same though. We're going to figure out some sort of a cutoff score and determine if that statistic that we calculate is in that critical region. Another big difference now with the F distribution is that critical values are based on two types of degrees of freedom. So let's look at those a bit more. Now, to look up our critical values, we need two different types of degrees of freedom. The first one is degrees of freedoms for a sample size, which is very much like what we've already been doing. So think back to our one sample t-test, we do n-1 because there was one group. When we did independent samples, there were two groups, so we did n-2. Now we do n-k, where n is the total sample size amongst all the groups, and k is the number of groups. So you're always subtracting one from each group. And this is called the within degrees of freedom. And sometimes it's denoted df with the subscript w. We also have degrees of freedom for the number of groups. So if you have three groups, we do k minus 1, 3 minus 1 equals 2. And this is the degrees of freedom related to the between group. This is our numerator. If you remember, the between goes on top and the within goes on bottom in that ratio that we are going to investigate. Here is one of the many F tables that are out there for the F distribution. Now we have up here degrees of freedom for the number of groups, and over here we have degrees of freedom for the number of people. So you will take into account your number of people, you'll look them up over here with your big N minus K, and you'll take into account the number of groups, K minus 1, up here. So what would the critical value be for an entire sample of n equals 10 and 3 groups? Give it a go. So first, let's look for our degrees of freedom between. We had 3 groups, so we're going to do k minus 1, which is 2. 3 minus 1 equals 2. So we will be looking in this column right here. We had 10 people total in the study, and we have to do n minus k, so 10 minus 3, we had 3 groups, equals 7. And we find this one right here. If we go across, the corresponding critical value is 4.74. So for degrees of freedom 2 and 7, our critical value is 4.74. Let's have a quick refresher of what sum of squares is again. It's like the precursor to standard deviation. So remember, we have all of our sample units, we subtract the mean, and we have these deviations. But remember, if we added them all up, they would just be 0, so we have to square them. So we square them all and sum them, and we get our sum of squares. Now, sum of squares is just another measure of variability. It's just like further up the line, hasn't evolved all the way into standard deviation. Remember, we go from sum of squares, then we divide by degrees of freedom to get variance, and then we square root and we get standard deviation. Finally is the ANOVA table. Now let's look at each column one at a time. We have the source of variability. So we're always trying to figure out, is this coming from between the groups, or is it just coming from within the groups, the individual difference things? Then we have sum of squares, which is like a measure of variability. Then we have degrees of freedom, which we already know what that is. Then we have mean squares, which is basically just variance. And then we have the F-statistic, which is basically just the amount of variance from between over within. It's that ratio that we're looking for. And we also have this row down here of the total, and it's just adding these two and adding these two. Let's go back to our ANOVA studying example. What are the degrees of freedom within, and what are the degrees of freedom between? Well, how many groups do we have? 3. We have to do k minus 1 to get the between group degrees of freedom. So we have 2 degrees of freedom in this example. Now how many people do we have total? We have 10, 10, and 10. Add all those together, we have 30 minus k, which was 3. So we end up with 27 degrees of freedom within. Run an ANOVA to test whether any of the true average scores differ for the 3 groups using a significance level of alpha of 0.05. And you are given the following information, because I would not make you calculate sum of squares for this. So we have 799.27 for the sum of squares between, and 158.90 for the sum of squares within. Step 1, stating those hypotheses. So of course our null is just going to say that all the means are exactly the same. There is no difference between them. Our alternative is saying that at least one mean is different. That is a very important distinction. We're not saying all three are going to be different, just that at least one is different. Step 2 and 3, we have an alpha level of 0.05, and we are going to run an F-test for our ANOVA. Step 4, find the critical values. This is just another type of F-table. There are many out there. We can look for, up here, we are going to look for our between degrees of freedom, and over here we're going to look for the within. So we had 3 groups, so k equals 3. What are our degrees of freedom for between? K minus 1, so our degrees of freedom are 3 minus 1 equals 2. So we're going to be looking in this column right here. Now all these extra things, these are just different levels of significance. We're going to be looking for the one that's 0.05. Now what are our degrees of freedom within? Well, we had 30 people minus k, so 30 minus 3 equals 27. So that is down here, that's 27. We look for the 0.05 that we're interested in, and here is our value right here, an F critical of 3.35. Also important to note, ANOVA always uses a one-tailed test formulation because F-statistics can only ever be positive. You should never end up with some sort of a negative variance or negative sum of squares, so it will always be positive. So here's our table again. Let's fill out what we know and then fill in some things based on calculations. We have our sum of squares between, what was given to us, and our sum of squares within, which was also given to us. We have our degrees of freedom, 2 and 27, and then we have the mean squares between and this F-test. So, first thing we need to do is take mean squares between by getting the sum of squares between, dividing by degrees of freedom between, and that evaluates to 399.64. We do the exact same with sum of squares within. We take our sum of squares within value, divide it by degrees of freedom within. Here's our equation. We end up with 5.89. So this is the table, and on maybe quizzes or different assignments, I might give you a table and have you figure out certain values, kind of like a Sudoku kind of game where some of them will be populated and some will be missing, and you have to figure out the missing values. Now, we have all this filled in, great, but we want that F-test. What's the F-test? Our F-statistic is 67.85. What was our critical value? Yeah, this is pretty big, so that's exciting. Where is most of the variability coming from in this example? Do you think it's all the people in each group are just very different from each other and there's a lot of variability amongst them? Or do you think this is coming from between the groups? So let's look again what an F-test is doing. It's comparing the between group variability over the within group variability. We're taking the ratio of that and we end up with 67.85. So where is more of that variability coming from? Between the groups. This is exciting as a researcher. Now let's draw our conclusions. We can reject the null hypothesis. There is enough evidence to reject the null hypothesis that the true mean score for each of these 3 groups is the same. Instead, we can conclude the true mean score is different for at least one group. This is again a very important distinction. We don't know if all 3 are different from each other, but we know at least one of them is different from the others. Now here is what the F kind of drawing would be, but don't need to draw this one because we're always going to be right-tailed. And we put that 5% probability over here, put our critical value, and here is our F-statistic way out here, so super significant. All right, so we have a significant F-statistic. Now what? We can conclude that the true mean score is different for at least one of the groups. Awesome! But do we know which one? Is it group 1 versus group 2, group 1 versus group 3, or group 2 versus group 3? Now what do we do? Pairwise comparisons. Now that we have a significant F-test, that is like our check mark, now we can go in and figure out, well, which of those group means is differing from the others. There are different ways to do this. Some are more conservative, meaning they are harder to reach significance, and some are more liberal, meaning that they're easier to reach significance. These are just 2 examples called Tukey's HSD and Bonferroni, and we're going to focus on Tukey's HSD. So what can we determine from this output? What is all this? First off, I'm going to let you know that half of this is a repeat. So if you look right here, we have negative 10, here we have positive 10. We have negative 11.7, positive 11.7, and so on. What this is doing is taking the difference, but in all directions. So book minus lecture, and then over here, lecture minus book. So it's the same information, just switch. Okay, we are taking the difference between people who just studied with the book versus lecture, and there was a 10-point difference between them, and you see that little asterisk right there. That means it was significant at the 0.05 level. We can also check this by looking at the confidence interval. Here's the confidence interval for the true difference between people who studied with a book versus lecture, and it was somewhere between negative 12 to negative 7. And what is missing from there? There's no 0, so we know it's significant. Now let's see book versus people who did lecture and book. An 11.7 point difference, also significant. What about lecture versus book? Well, we already did that one. See, we have the negative 10, here's the positive 10, so we don't need to look at that again. We know that's a significant difference. We need to look at lecture versus lecture plus book. That's the other pair we need to look at. And here we see a difference of negative 1.70. Now, first off, we don't have the little asterisks. And if we come over here, we see that the true difference between studying with a lecture notes and lecture notes in a book is somewhere between negative 4 and 0.99. Let's look at lecture versus book. But wait, we've already seen that one. We know that that's going to be significant. It's just that now we are subtracting book from lecture, so we're going to have a positive value instead. Over here we are subtracting lecture from book, that's why it's negative. The only other pair that we need to look at now is lecture versus lecture plus book. And we see a negative 1.7 point difference. Now, is that significant? I don't see the asterisk. Here's also the actual p-value, which is 0.277. We know that's not significant. But we can also look at the confidence interval. The true difference between studying with the lecture notes versus lecture notes in book is somewhere between negative 4 and 1, meaning that you can study with the lecture notes and you will either get 4 more wrong when compared to the ones who study with lecture and book, or 1 more right. Now the fact that it has 0 in it means that this is not significant. We don't know if you're going to do any better or worse studying with a book and the lecture notes versus just the lecture notes. So this was not statistically significant, but the other two were. Here is that summary that book versus lecture notes, significant. Book versus book plus lecture notes, also significant, but the difference between studying with your lecture notes plus a book, just lecture notes, was not significant. And again, these zeros here let us know that. Drawing conclusions, again. The overall F-test was significant. Now from the pairwise comparisons, we got this information that the book-only group had significantly lower mean score than the lecture notes and lecture notes plus book. There was no difference in the exam scores between lecture notes versus lecture note plus book. This is how we would write it in APA notation. We would have F, and we have our degrees of freedom between, so 2. Then we write our degrees of freedom within, so 27 equals 67.8. And we have a p-value less than 0.05. Now again, true APA would actually put the actual p-value here, but for our sake, this is fine. Practice! Television viewing. New research suggests that watching television, especially medical shows, can result in more concerns about personal health. Surveys were administered to 18 college students, measuring their personal health concerns on a scale of 0 to 10. For the following data, students were grouped based on their television viewing habits. Test whether the personal health concerns are the same for the 3 groups using 0.05, and we are given this information. Let's go. Step 1, state the hypotheses. All the groups are the same. At least one of the groups is different. Step 2 and 3, 0.5 and F-test. Step 4, find the critical values. We have 3 groups, so that means we have 2 degrees of freedom between. Looking in the second column, we had 18 people, minus 3 equals 15, so we're looking right here at 0.05. Our critical value would be 3.6. Now, using the information we have, let us populate our little table here. Pause me and give this a go. See if you can figure out mean squares within and the F-statistic. You can do it. Do it. Come on, do it. All right, let's go. Here is the table filled out. If we take our sum of squares between 36.99 divided by 2, we get 18.495. If we do the sum of squares within, 49 divided by 15 equals 3.267. You divide those two and you get 5.66. Is it significant? Yes, indeedy, we have F-test. 2 degrees of freedom between, 15 degrees of freedom within. Our F-test was 5.66. Our p-value was less than 0.05, so we get to reject that null hypothesis, and we can conclude that at least one of the group means differs from the others. Now, after this point, you would typically continue with pairwise comparisons, but we're going to move on. We spend a lot of time looking at the differences between things, using our z-test, t-test, or ANOVA. We're going to switch gears next, and we're going to look at the association and the relationships between some variables. Up next, correlation. I will see you there. ANOVA in R. Now let's look at some real data about bug bites. We've looked at this data set before, but we're going to analyze it a little bit differently this time. Mosquitoes are an annoying fact of life, and we must all live with. Let's compare the effectiveness as quantified by the number of bug bites of 6 different bug bite prevention products. We have natural oils. We have citronelle. We have DEET spray. We have citronelle spray. We have picaridin. And we have nothing, which will be our control. Now I should note that the data that we are going to use is actually real, but I have made up these names just so they're not just group 1, group 2, group 3. It'll make it more interesting, but I am not saying that any of these are more or less effective than others. First, let's look at some descriptive statistics. Just by looking at the descriptive statistics, which product looks like they might be significantly different from the others? Which looks like it might be the best? Is there a best? So it looks like the group that had nothing, the control group, the natural oils and the citronelle candles have higher numbers than these 3 groups. So maybe those 3 will be significantly different from these 3. Not sure. Let's go find out. So this is the ANOVA output from R. We can see that our between group, degrees of freedom, is 5, so we had 6 groups. We have 66 degrees of freedom within, meaning we had 72 observations because 72 minus 6 is 66. Our F value is 34.7, which comes from dividing the mean squares between by the mean squares within, this divided by this. And our p-value is very significant. So, what is our conclusion, and what should we do next? When we have a significant F value, we know that at least one of the groups differs from the other, but our ANOVA does not tell us which groups. We need to conduct a pairwise comparison like Tukey's HSD. Here is the output for our pairwise comparisons. Now, I know there's a lot. It's because there are 6 groups, so we have a lot of pairs that we have to evaluate. But let's just look at a few real quick. Let's see, citronelle versus natural oils. Remember, they didn't look like they were very different. They both had quite a few bug bites. So we have a difference of 0.83 between them. And we can see here that it is very not significant. That is huge. We're trying to get below that 0.05, and this is 0.99. You can also see it in, this is the lower bound, and this is the upper bound of a 95% confidence interval. So we see negative 3.6 and positive 5. So the difference between them is somewhere between negative 6 and positive 5. Very not significant. Now let's look at DEET and natural oils. We see that DEET has 12 bug bites less on average than the natural oils. We can also look at the confidence interval to see that it does not contain 0. We have negative 17 to negative 7. So that's saying that the true difference between DEET and the natural oils for mosquito prevention is somewhere between 17 and 7 bug bites. But either way, you're going to get less bug bites with the DEET. And here's our p-value, super duper significant. And you can go through the rest of these and figure out which ones are significant. You can also just, of course, look right here and see which ones are less than 0.05. And here I've marked out all of the significant and insignificant ones. Now let's summarize all that stuff from the table. We had this less effective group, which was comprised of the citronelle candle, natural oils, and the control group. All 3 of them did not differ significantly from each other. Then we had this more effective group here, which was the DEET, picaridin, and citronelle spray, and these did not differ significantly from each other. But this group and every single one in this group did differ significantly from every single one in this group. So if you don't want bug bites, you should go for the DEET, picaridin, or citronelle spray. Again, all of these names are made up. There are some actual sprays that somebody tested many, many years ago, but it's not actually DEET and natural oils and all of that. So here is all of the code. So compared to what you would have to do by hand, this is incredibly easy. You can run a quick ANOVA just to check something if you feel like it. So first, I load in the data, which is that insect sprays that's already in R. You just call it bug spray for your data. This is not important. This is where I'm renaming all of the different variables, so you certainly don't have to do that. And we can describe, but using this fancier function called describe by with a capital B. And we can say bug spray, and we're going to say describe them by the different types of spray. So it's going to give us descriptive statistics for each group, and we saw that a little bit earlier. And to run the ANOVA, this is all you have to do. You have bug bite ANOVA. We're going to save our object into here. That is AOV, that's the function for the ANOVA, parentheses. We have count, which is the number of bug bites. That is our outcome variable that we're interested in. And we're going to use this little tilde, and we're basically saying explain the number of bug bites by the type of spray. And we're going to tell it that the data is bug spray. Then you run that really quick. Now you ask for the summary of this object, and it will give you that ANOVA table that we looked at. And if you have a significant F-test, then you can do the pairwise comparisons, and you just say Tukey's HSD, parentheses, the object that we made from our ANOVA. And that's all you gotta do. It's a lot quicker and easier technically than doing it by hand. So try this out. Use the insect spray data set that's already in R and run a quick ANOVA. You can do it. You're gonna feel good about it. I feel good for you. See you in the next one.